Today I want to tell you about something completely different, which is all about black holes. And it's part of what Evelyn Gates began last week, Einstein's weighty legacy. So tonight's talk is black holes from A to Z, but missing a lot in between. And you'll have to ask about that during the questions. So what I want to do is I want to start by telling you in the first part how there's no escape. At least in the appropriate situation, what goes up must come down. Later on, after the first set of questions, we'll talk about seeing or perhaps making black holes. And finally, we'll get to some really problematic pieces of physics, evaporation of black holes, and something called the information loss paradox. But let's start with this idea that there's no escape. What does that mean? Well, of course, if we're used to the idea that what goes up must come down. We use it if you're a juggler, of course, you use it all the time, but you use it if you're playing a ball game. We use it in our everyday lives in so many ways. We know what's responsible for that. It's the law of gravity. We've known how that works for a few hundred years. We've got better and better about understanding that, moving from Newton in the 1600s to Einstein in 1916, teaching us about general relativity. And 100 years later, we've explored that theory of general relativity in great detail, and so far have no clear evidence that there's anything wrong with it. It works for all the, at least everyday phenomena, by which I mean phenomena on the scale of the Earth and the solar system that we know about. Now, when I say what goes up must come down, I mean if I throw something up, I can be pretty sure that a couple of seconds later it's going to land back here, and if I've done it right, I can catch it. That works on larger scales too. If you throw something up from the surface of the Earth, like a ball or a pineapple or a duck, it will come back down if you throw it up at the right speed. So not only does our theory of gravity work on these small scales of throwing up balls to juggle them, or throwing a baseball, or hitting a baseball, but it works on these much larger scales of planet Earth. If we throw things up, they come back down. This is something that people sometimes don't realize when they think that it would be fun to celebrate some event by shooting bullets up in the air. I'm sure you've seen that on the news. And if you've wondered what happens to those bullets, it is in fact true that what goes up must come down. And that's not so good, because although the bullets do go up at about Mach 5, at 5 times the speed of sound, they don't come down that fast. They only come down fast enough to kill you. And that has been realized by some people. For example, here are a group of Filipino policemen, and they've been ordered to tape the ends of their guns so that they can't shoot them during the New Year's Day celebrations, because their officers realized it was not a good idea to shoot your gun up in the air, because those bullets had the potential of coming down and hurting people. So that's one way that what doesn't go up won't come down, is a way of stopping things from coming down. Of course, we have another way of making things go up and not come down, and that's making them go really, really fast. So when we throw a baseball up, it's only moving a few meters per second, a few feet per second, not particularly fast. We have to make things go much, much faster than that in order to stay up in the air. How fast? Well, if we want something to go into orbit around the Earth, like the space shuttle or a satellite, it has to be moving not at Mach 5 like a rifle bullet, a really fast bullet, but more like Mach 23. Okay? So rifle bullets are nowhere near close enough, about 5 miles a second. Okay? So kind of imagine something that gets from here to downtown in a second. Something like that if you send it around the, if you shoot it the right way, it'll go around the Earth and it'll keep going around the Earth. Okay? So there are lots of places in the world or lots of companies now even that are building rockets that can do that can go into orbit, taking payloads up that go around and around the Earth, typically in low Earth orbit about 90 minutes or so, geosynchronous orbit in a day. Okay? So we can send things round and round the Earth, like our rockets. Of course, things like the moon also go round and round the Earth. They're just falling. But we can also send things out away from the Earth. And to do that, they have to go even faster. And that's called the escape velocity. Okay? So the escape velocity means the speed at which something can escape from the Earth. And that's Mach 34. Okay? So we've gone from Mach 5, which is a rifle bullet, to Mach 20-ish, which is something orbiting the Earth, to Mach 34, about 11 kilometers a second, about 7 miles a second. Now, these sound like high speeds, but the speed of light is about Mach 1,000,000. So from the point of view of physics, like relativity and things like that, these are actually very, very slow speeds. 11 kilometers a second or 7 miles a second versus 300,000 kilometers a second or 186,000 miles per second. Okay? So to escape the Earth does not take, although it's fast for us, we think of a rocket as moving very, very quickly. In fact, on the scale, absolute scale of velocity in which the speed of light sets the speed limit, these things are dawdling along. Now, as I said, the escape velocity from the Earth is only about 10 kilometers a second. We can make the escape velocity from the Earth would be higher. In other words, we would have to shoot something up much faster if the Earth were denser. So if we could take the Earth and press on it really hard, I don't suggest that we do this. Our gravity, we would all feel much heavier. But now if we make the Earth denser, then if you try, you'd have to throw it a lot faster. Okay? So a denser Earth means a higher escape velocity. But things like the Earth, things made of rock, don't tend to be any denser than the Earth. The Earth is made of stone. We don't find stones that are that much denser than the rock on the Earth. Okay? What other objects might have higher escape velocities? Well, here's the sun. So if we have a much more massive object, then it tends to have a higher escape velocity. In other words, in order for something, if you were standing on the surface of the sun, of course it would be quite warm. You also wouldn't be able to stand because it's not solid, but let's suppose you were hovering there. Then in order to throw something up and have it not come back and hit you on the head, you'd have to throw it up at about 1,000 kilometers a second. Almost a third of a percent of the speed of light. Okay? So big, massive objects have higher escape velocities. It's harder to get things up out of them. Okay. Now, if we could take the sun, so what I'm showing here is the size of an object, like the sun, versus the escape velocity. So here's something like the sun that has a size of about 700,000, a radius of 700,000 kilometers, or about 450,000 miles in radius. What happens if we could take something like the sun and compress it, make it even smaller? Then what would happen is, as we made it smaller, the escape velocity would be higher and higher. Okay? Now, you notice this dashed line here. That dashed line represents the speed of light. Okay? So what this says is, if we could just compress the sun enough, then the escape velocity from the surface would be larger than the speed of light. What does that mean? It means that if we could, on the Earth, we can throw objects up and they'll come down. But if we throw objects up fast enough, they don't come down. And certainly if we shoot light beams, if there wasn't a ceiling here and I shot this laser beam up, it would not come down, right? It would go off into space at the speed of light. But if we could take something like the sun and compress it to a small enough size, then in fact what we would get is that we could, if we tried to throw something up like a ball, no matter how hard we threw the ball, it would always come down. And in fact, if we shone a flashlight or a laser beam straight up, that laser light would never leave the star. Okay? It would never manage to get away. In fact, if I tilted it just a little bit, it would go up in a nice arc, and it would come right back down. So we shoot a light up, and it comes right back down. And we call this object a black hole. Okay? Now, the idea of a black hole has been around for several hundred years. But the name black hole was given by this fellow. His name is John Archibald Wheeler. He was a professor at Princeton for many, many, many years. His main contributions were not so much, well, he made many important contributions to physics, but some of his most important contributions were in coming up with kind of clever names for things, like black holes and wormholes and quantum foam. But also he was very famous as a teacher. And probably his most famous student is a fellow named Feynman, who many of you I'm sure have heard of, Richard Feynman. But he had many, many students who went on to much greater fame than he as a scientist. And I remember him as when I was a young postdoc at Princeton, and he had come back from, in his retirement from several years at the University of Texas. And he was always the most approachable of the famous old physicists. You know, he would never sit at the head of the table, always in the middle of the table. He would always talk to the young people. And he was really a delightful man. And that was his reputation as this very creative, wonderful teacher, always interested in talking to the young people. And maybe that's why Feynman, who was certainly an iconoclastic fellow, had such a great time working with him. So he gave this object the name black hole. Now, I said we had to take the sun and compress it. How small do we have to compress the sun? Well, there's a name for how small. It's called the Schwarzschild radius, after a fellow named Karl Schwarzschild, this fellow. And so the question is, how big is this object? So if we take the sun and compress it, how small do we have to compress it in order to make something that has what's called an event horizon? In other words, some place from which you cannot shoot, inside of which you cannot shoot out a light beam. So if this were the sun and we were out here, we could get things out. But if we were inside the event horizon, inside the Schwarzschild radius, no matter what we did, we could not get even a light beam out. So it turns out that the Schwarzschild radius of an object is proportional to its mass. The larger the object is, the larger the radius. For the Earth, it's a few millimeters. So if we could take the Earth and compress it to this size, we would make a black hole. Okay? If we could take the sun and compress it to a few kilometers, so kind of the size of Cleveland Heights or Manhattan or something, then we would make a black hole. Now, we'll talk in a little bit about black holes that are millions or even billions of times the mass of the sun, and we would have to compress them to a few million kilometers. And these sounds like a big distance, but imagine something that is 1,000,000 times the size of the sun compressed to something, a volume that's even smaller than the sun. So what have we learned? We've learned that if we take ordinary objects like the Earth or the sun, then we are able to throw things up out of them at some escape velocity that typically tends to be, from the Earth, 10 kilometers or so, from the sun, 1,000 kilometers, but still very small compared to the speed of light. But if we can compress these objects to much smaller sizes, or if nature can do it for us, then we will get an object from which even light can't escape, and that's what we call a black hole.
Is there a difference between the mass and the density in determining which ones? Well, what works?
So the more massive the object, the less dense you have to make it to make a black hole. Okay? So if we took the Earth and compressed it down to 8 millimeters, if I remember correctly, that is much denser than taking the sun and compressing it to 3 kilometers, and much, much denser than taking something that's 1,000,000 times the mass of the sun and condensing it to 1,000,000 kilometers. Okay? So really big black holes actually aren't that dense at all. In fact, for a long time, we wondered whether we might be inside one, and we wouldn't notice necessarily.
You said earlier, you gave a picture of the curve with the speed of light.
Right.
And at that point, it sounded like if it was a black hole, then any object out there in space would be drawn inexorably and unescapably to it. But isn't it true that the event horizon for a small black hole is very, very small? So you've got to be real close before this effect happens.
Exactly. So this is a common misconception. People think, oh, if there's a black hole, it's going to suck everything in. So for example, if we took the sun and turned it into a black hole, we'd get very cold because the light wouldn't come out of the sun and the heat. So it wouldn't be very good at heating the Earth. But the Earth would continue to go around the sun in exactly the same orbit as it does today. So black holes are only dangerous if you get close to the event horizon. Okay? And the event horizon of a black hole the mass of the sun is 3 kilometers. Well, that's really close, considering the sun is 700,000 kilometers in radius today. Okay? So we're really talking, the sun's nowhere near a black hole. Okay? So yes, you have to get very close to an object before its gravity becomes really, really strong. A black hole the mass of the sun at the center of the solar system behaves gravitationally just like the sun does for something far away like the Earth.
I think they stole my thunder. I think what you're describing to me sounds like super heavy-duty gravity. That's it.
Well, it's super heavy-duty gravity when you get really close.
Yeah.
Right. So the closer you get to an object, the stronger its gravitational pull. If you're twice as close, you have 4 times as strong a pull. Okay? So we can't get very close to the Earth. What do I mean? I mean the center of the Earth is about 6,000 kilometers away, about 4,000 miles away. Okay? That's as close as we can get to the center of the Earth. If we made the Earth a centimeter, this big, then we could get that close to the center of the Earth, and that's why the gravity would be so strong.
Right.
Okay? Right now, if we want to get that close to the center of the Earth, we have to dig a tunnel, and then we'd have to go down the tunnel, and when we got this close to the center of the Earth, we'd discover that all of the mass of the Earth was above us instead of below us, and that's what it wouldn't exert a strong pull towards the center. Okay? So the reason a black hole has a very strong gravity is you've pushed all the mass into a very small region, very small volume, and then you've gotten really close to it, and now it has really strong gravity. The next part of the talk, I'd like to talk about how we would see or make and then see black holes. And so you might be surprised to know that it can be difficult to tell that you have a black hole. So how might you tell that you have a black hole? Probably the easiest way would be to jump in. Now, if you jumped into a black hole, what would happen? Well, you would lose touch with the people outside. Actually, they would lose touch with you. You wouldn't be able to send them messages because once you jump into a black hole, you have nothing that you can send out. You can't send letters. You can't send postcards. You can't even flash messages with your semaphore or with your laser beams. No one will see those messages, right? So if we have a black hole and we send someone jumping in, you may think it's a lot of fun, but you're going to lose touch with all your friends. They can send you messages, by the way. They can tell you about their life and how everything's going out here on planet Earth, but you can't answer them. In fact, what we would see would look something like this. We would see, first, the person getting redder and redder. And I'll explain why in a minute. The second thing we would see is them freezing in position. And finally, what we would see is them fading from view. So why do we see each of those things? Well, we see them getting redder and redder because the light that they emit right? So we're looking at them from some reflected light, or maybe they're shining a light on themselves so that we can see them. That light has to climb out of the gravity of the black hole. Okay? And the closer they get to the event horizon, the more it has to climb. When it makes that climb, it loses energy. Just like if I take a ball and throw up the ball, what happens? The ball starts with lots and lots of energy, and as it goes higher, it loses energy, and then it stops and turns around. Well, as they shine a light up, the light loses energy. And what happens? Light, as it loses energy, gets redder. Okay? So the first thing that happens is, if you watch, the person jumping in gets redder. The second thing is that they kind of freeze on that event horizon. They appear to, if we could watch their watch, if they didn't have a digital watch, but one of those old analog watches, their watch would slow down, or it would look to us like it was slowing down. It would slow down and slow down and slow down, and there would be a point where it would appear to stop. Okay? So looking at them, there'd be a point after which we can't see them, you would think. So you would think that they would disappear from view, but actually what would happen is that everything would appear to go more and more slowly, and they would appear to freeze. Now eventually, what would happen is that they would also fade, and that's only because they are sending out particles of light, photons, at a finite rate. And eventually, the time between successive photons gets longer and longer and longer, and we just never see them. By the way, they wouldn't notice necessarily anything terrible happening to them. They wouldn't feel like they froze. They would feel like they just jumped into the black hole and passed through the event horizon. Okay? And we'll see a caveat to that in a minute. So the first thing is, you could send someone in, and if you lost touch with them, that would be then you would know that they probably had gone to a black hole, although maybe they just hit something and died. But they would know that they had gone into a black hole. They could figure that out. So the first way is jump in and lose touch. The second way is get too close to a small black hole. Because what happens if you get too close to a small black hole is, suppose I jumped into a black hole, suppose this was the surface of a black hole, then the gravity at my feet would be stronger than the gravity at my head, because my feet would be closer to the center of the black hole. That's not a good thing. So just like what happens to these letters, where they get kind of ripped apart, the person jumping into the black hole, they would get stretched. And that's a real thing, and that hurts. Okay? In fact, if it's a small enough black hole, they'd get ripped apart, which is really bad. If it's a big black hole, actually, it wouldn't be so bad, and they could do this. You could do this. So a 10 to the 9th solar mass, a billion solar mass black hole, you could probably safely jump into it if you felt like it, and if you could get to one. So we have now two ways of finding black holes. Unfortunately, neither of them terribly practical. So here's a third way. Look very carefully, and if it's nothing else, it's probably a black hole. And this is how we know there are black holes. This is the way in which we infer that there are black holes out there. Okay? So, for example, when a star becomes a black hole, let me tell you how that happens. So we start off with a star that is burning hydrogen. Okay? It's turning hydrogen into helium. It's taking hydrogen atoms, fusing them together to make helium. That lets off lots and lots of heat. It's basically a controlled thermonuclear explosion. And that heat stops the star, like the sun, from imploding. Eventually, the star runs out of hydrogen. And when it does that, it starts burning helium, and it's even hotter at the center, and it actually expands and gets redder, and that still stops the star from imploding. And if the star is big enough, if it's massive enough, it will keep burning up through the periodic table, one element after another, changing size and color, until eventually it has an iron core. A core made of iron and other elements near iron. And once it does that, it really can't efficiently burn into anything else. And what happens is that the exterior of the star explodes outward, and the interior of the star collapses. And if it was a big enough core of the star that collapses, what it leaves behind is a black hole. Our sun will not do this. It's not big enough. But larger stars, we believe, should do this. They should leave behind a black hole. Well, I still haven't told you how you know it's a black hole. And really, the only way to know it's a black hole is by a process of elimination. So for example, suppose it was something less dense than a black hole. The next less dense thing is something called a neutron star. A neutron star means take a nucleus that's like we have at the centers of normal atoms, but imagine it much bigger, like the mass of the sun, or twice the mass of the sun. So instead of being 2 miles in radius, imagine it's 7 or 8 miles in radius. 10 kilometers instead of 3 kilometers. Then we could have something orbiting that neutron star. Okay? And a couple of things, we could watch it orbiting the neutron star, and if it hit the neutron star, it would be kind of like this. It would notice. It would hit something hard. The neutron star has a solid surface. Okay? So the neutron star, you hit the neutron star and you go kaboom. That's not what it's like to hit a black hole. Hitting a black hole means you spiral into the black hole and you don't hear anything. There's no solid surface there. You just pass through the event horizon. So in fact, what we do is we watch. This is a photograph of something called Cygnus X1. Okay, it's a star about 6,000 light years away from the Earth. And we've watched X-ray globs of stuff fall into the black hole, emitting lots of X-rays as they go along. And when they fall into the black hole, nothing special happens. They just keep emitting X-rays. They don't go smash. Okay? And from that, we infer that this is not a neutron star or anything else. Because if they hit something else, they would go smash. So as the matter falls into the black hole, it behaves like something that's falling into a black hole. Namely, nothing terribly violent happens at that moment. Okay? And so we think it's actually a black hole that's about 15 times the mass of the sun. Okay? And 15 times the mass of the sun and about 30 miles in radius, about 60 miles across. So imagine taking something 15 times the mass of the sun and compressing it to the size of Cleveland. That's what this is. Now, the other thing we can do is, as I said, we can watch things go around and around some object. And by watching them go around, we can learn how big, how massive the object is. And we can also learn how close these things going around are. And we do that to objects like this big, heavy object called Sagittarius A that's at the center of our galaxy, okay, a few thousand light years away. And there's an object there that is about 4 million times the mass of the sun. Okay? And that object is really small. Okay? Really small meaning we know that it's much smaller than the distance from the Earth to the sun. Okay? We know of no other object that could possibly be that small and that massive. We know that neutron stars, they only get up to about 2 times the mass of the sun. After that, they have as far as we can tell, they should just implode. It could actually be a cluster of stars just orbiting each other. It could be that, but those only would last a few years, maybe a few thousand years, okay, which is not a very long time in a galaxy that's many billions of years old. Okay? So what this almost certainly is a black hole that's 4 million times the mass of the sun. Okay? And we can see X-rays coming out of the center of the galaxy when things fall into that black hole. Okay? We also look very much farther away at very distant objects that are called quasars. Okay? These are incredibly bright, and what they are understood to be are black holes swallowing massive amounts of gas in very young galaxies. In fact, we think that most galaxies started off with black holes at their center, kind of like the one at the center of the Milky Way, and matter was falling into them and then being blown out Some of it comes in, some of it's being blown out before it gets into the event horizon, before it falls all the way into the center. And we've seen about 200,000 of these objects. We think there are probably about several million of them out there to be seen. Okay, we haven't looked far enough or to dim enough objects. It should look something like this: a huge swirl of gas orbiting this very, very massive black hole at the center of a galaxy. Some of the stuff shooting up out in jets, some of it being ejected out in this way. And these are very, very, very bright. Okay? We can see them across the entire universe. The black hole at the center of our galaxy is actually a pretty small one at 4 million times the mass of the sun. So other galaxies have black holes that are 1 billion times the mass of the sun. Okay? And as far as we can tell, pretty much every galaxy went through a phase in which they had every big galaxy went through a phase in which it had a black hole like this, swallowing gas and stars and shining really, really brightly. Okay, so we've now seen astronomical black holes, the masses of kind of the mass of the sun, 10 times, 15 times, black holes, the masses of millions or billions of times the mass of the sun. The other possibility, and those are the astrophysical black holes we see, the ones out there in the universe. But what we'd love to do is to actually make some black holes, because then we could really study them. So the place that we had some hope of doing this, or have some hope of that, is actually where I'm spending the year right now. My office, I'm trying to think, my office is somewhere over here, and I live somewhere over here. And this is called the Large Hadron Collider in Geneva, Switzerland. You can see Mont Blanc there in the background, and this is Lake Geneva. And this is about 100 meters underground, this ring. It's not a yellow line painted on the surface of the Earth. Okay? And there are little rings here in which they accelerate protons and then inject them into this big ring, some of them going this way and some of them going this way. And then they smash them into each other, okay, with enormous amounts of energy. Okay? Energy equal to about 7,000 times their mass. Remember, E equals mc squared, so mass is a type of energy. But they have, when they smash into each other, they have 7,000, actually today, nowadays, 8,000 times their rest mass energy in their collision. And what they can do is, when those two protons come in, one from each side at a very rapid speed, one could hope that they would smash into each other and make a black hole that would swallow the Earth. At least that was the fear. That's not likely to happen. What instead is likely to happen is that they would make a black hole that would fall apart and eject particles in every direction. And actually something that we did here a few years ago is write a computer program to tell them what it would look like. How would those particles come out, in what order, and what would it exactly look like, so that these huge detectors, can you see this person down here? It's actually very hard for me to see them from here. Here's a person, and here's a detector actually before most of the stuff has been stuck into it. These detectors are bigger than this room. Okay? And the particles, the collision happens somewhere in the middle here, and then the particles go flying out, and you have to look to see that you had a black hole. Now the good news is that if you made such a black hole, it would not destroy the Earth. It would actually disintegrate before it traveled the width of an atom. The bad news is, so far they haven't made any black holes.
Last week we heard about gravitational lensing past massive objects, clusters of galaxies and stuff. Does a black hole lens, or does it swallow everything going even near it? Or can you lens something in back of it?
A black hole would lens just as well as the sun. So remember, if you take something the same distance away from a black hole, which has a mass equal to the mass of the sun, then the thing passing by doesn't know the difference between the sun and the black hole. Okay? So think of the sun as a gravitational lens. What does that mean? You have the sun there and things that pass by, light that passes by the sun, not through the sun, outside the sun, gets bent. Right? So if we replace the sun by a black hole that's much smaller, those same light rays that are far away from the black hole would be bent in exactly the same way as they would be if the sun was there. So yes, it acts just like the sun as a lens. Now in addition, you can have light rays that are much closer now, right? Because the light rays that would have hit the sun, they'll miss the black hole, most of them. And they can do all sorts of interesting things. If you get close enough, they can actually orbit before they leave. They can go around once or twice or many times. If the black hole's spinning, other interesting things can happen. I'm talking mostly about black holes that are sitting there, but black holes can also spin. And that will change exactly how the light behaves. So yeah, they can make really great gravitational lenses, very interesting gravitational lenses. I don't think we've ever seen, and I'm not sure about this in fact, I don't think we've ever seen gravitational lensing by a black hole where the light came close enough to really matter that it was a black hole and not something else. Okay? But I may be wrong on that, and certainly that's something people hope to see.
As mass enters the black hole, A, what happens to it, and B, does the black hole get bigger?
The second part is easy, yes. Right? You throw something into a black hole, and the black hole gains mass. Right? So that's the easy part. The second question, what happens to something when you throw it into a black hole? And there are some complications, but basically, so as remember I said, we could jump into a black hole and we'd be perfectly happy. We wouldn't be happy forever, because all roads lead to the center of the black hole. And the most likely story is that at the center of the black hole is a bad place. It's called a singularity. That's at least in what's called classical gravity. There's a place that doesn't belong to space. It's kind of a point missing, and you don't want to get there. But you will. Okay? Now, we're not sure that that's really true. It may be that quantum mechanics would actually soften that in some way. But no one really completely understands the property of what happens to singularities when we marry quantum mechanics to gravity. And part of that is because, as I'm going to tell you, we don't actually know how to marry quantum mechanics and gravity. In part, because of some things I'm going to tell you about black holes.
So these black holes are concentrating energy around them outside the event horizon and mass around them and also in them. What about dark matter? Do they concentrate dark matter also?
When you say concentrate, what can happen is that stuff can kind of get near a black hole and form things like an accretion disk, a disk of matter that surrounds the black hole. That's what we have in quasars, and then things can fall into them. Or in that Cygnus X1, we can get a disk of stuff falling in. Dark matter, it'll depend a lot on the properties. Certainly, if dark matter passed close by and in such a way that it would hit the black hole, then it would go into the black hole and be swallowed by the black hole and add to the mass of the black hole, just like if we jumped in. Remember I told you that nothing can come out of a black hole? That's not true. And that was, everyone knows Stephen Hawking for being on television programs and writing books. But as a physicist, probably the most important piece of work, or at least the most well-known piece of work of physics that he did, is to understand the process of black hole evaporation. Along with other people, in particular a fellow named Yakov Bekenstein. But we're going to talk about something called Hawking radiation. And this is what we might call a quantum mechanical escape clause from the statement that nothing can ever escape a black hole. So how does this work? Well, as some of you have heard me say before, nothing is actually a kind of complicated place. So the vacuum, empty space, is much more complicated than just space with nothing in it. This is our standard picture of nothing. You'll notice that there's nothing there. Okay? Quantum mechanics tells us that that's not a great picture of nothing, really because of something called the Heisenberg uncertainty relation. Things are popping in and out of existence all the time. So it's a much more grainy view, or maybe this is even a better picture, that there are things popping in and out of existence all of the time. So that is what nothing is like out there in empty space. Well, what about near a black hole? So the standard picture of the space around a black hole is that there's nothing there. And if that was true, then indeed black holes would not evaporate. But remember, this is the quantum picture of space around a black hole, with things popping in and out of existence. So let me put the black hole there, and here are these things popping in and out of existence. But occasionally in that pair, one will fall in to the black hole. Here's the black hole. It's hard to distinguish from the rest of space. But this one has fallen in, and this one has gone out. What does that mean? If it's gone out, then it's carried some energy away from the black hole. It's out here, it's carrying energy, and in fact, it can travel all the way out to infinity, out to here where we can see it in principle. And so what's happened is the black hole has lost some energy. Okay? It's kind of taken that energy, it seems like, from this quantum mechanical process going on around the black hole, this quantum mechanics of the vacuum, and that allows the black hole to lose some energy. So what has happened is that something has left the black hole, namely some radiation, and we call that Hawking radiation. After this fellow, and this is actually a picture of him giving a talk at Severance Hall a couple of years ago. And this is a picture of him at a meeting that we organized a couple of years ago. Probably the most famous scientist alive today. So, as I said, before the black hole had some mass, afterwards it has some other mass, and since it emitted some energy, its new mass must be less than its old mass. In other words, we started with a black hole, it emitted some Hawking radiation, and now the black hole is left with less energy. Okay? So black holes are getting smaller. So the black hole loses mass, and we call that black hole evaporation. So really, Hawking radiation tells us that black holes glow. They're not black, they glow. They have a temperature called the Hawking temperature. The bigger the black hole is, the colder it is. And the bigger the black hole, the dimmer it is. Now, that's unfortunate, because the black holes that we get to see are quite big, right? They're things 15 times the mass of the sun, 4 million times the mass of the sun. And so a black hole the mass of the sun has a temperature of about 1/100,000th of a degree above absolute zero. That's very cold. A black hole at the center of our galaxy has a temperature of about 1/100 billionth of a degree above absolute zero. And we might have some hope of seeing something like this. This even would be more difficult. But the universe itself is glowing with a temperature of about 3 degrees. It's filled with the afterglow of the Big Bang, and it hasn't cooled off that far yet. It's only cooled down to 3 degrees above absolute zero. So these black holes are much colder than the universe. And so in fact, they're absorbing energy from the universe much faster than they're emitting it, but it would be very hard to see this radiation with all this noise. Okay. So, black holes, we can expect for them to glow, but it's going to be very hard to see it. Now, that does explain, though, how if we manage to make black holes in our collider, they can fall apart, because those are really, really tiny black holes, incredibly tiny black holes. They would be very, very hot. They would actually glow and emit particles that are very energetic, and they would fall apart very, very quickly. Okay? And that's good, because that way they won't swallow the Earth. So that's why it's safe for us to try to make black holes, because if we succeed, they will fall apart, as I said, faster than it takes, before they could cross the diameter of an atom. Okay. Now, this process of black holes evaporating leads us to an important paradox. A paradox is when we get two different answers, or two contradictory answers, from thinking about a problem in two different ways. So it's called the information loss paradox. And to think about the information loss paradox, let's start by thinking of a book. So I have here a copy of Hamlet turned to a famous page. And I know this is terrible, but we are going to throw the book into the fire. Now, it's not quite as bad as you think to throw a book into the fire, because it turns out that if you are very, very careful and very observant, you can actually read the book as it's burning. It seems very hard, and it is. It's not very practical to do it, but we can do it in principle. Okay? It's kind of like throwing a book into a document shredder. Now, if you threw a book into a document shredder and then someone gave you enough time, you could probably reassemble the book from all those, those shreds. You wouldn't want to have to do it, but if there was some really good reason to do it, you could. Throwing a book into a fire is actually like throwing into a document shredder. The information that was in the book comes out, but it comes out in this terribly complicated way, which is how the different particles of light are, that when they come out, what direction they come out, what energy they come out with. You could, in principle, put it all back together, but please don't ask me to do it. But as what's called a Gedanken experiment, a thought experiment, we can realize that throwing a book into a fire preserves the information. And in fact, quantum mechanics tells us that it must. Okay. Now, what about throwing a book into a black hole? So here's our black hole in the middle of space. If we look carefully, we can see it. Remember, we said we have to look carefully to see black holes. And here's this book ready to fall into the black hole. There it goes, but the letters don't come out. Once the black hole the book has gone into the black hole, the only thing the black hole knows is how much mass that book had. It also knows about if the book was charged, if it had electric charge, and if the book was spinning, it would know about that. But that's not very much information. It's much less than, Hamlet's speech, or the information that if you threw a dictionary in there or an encyclopedia. So when we throw things into a black hole, what happens is we throw the book into the black hole. Watch what happens. Here's the book. We throw it into the black hole. Here's the black hole. Stuff comes out. Slowly, the black hole gets smaller. Let's see. Come on, get smaller. Black hole gets smaller. There we go. The black hole gets smaller and smaller and smaller and smaller. And when we're done, the information in the book is gone. So we threw the book into the black hole and lost all the information in the book. Now you might say, why should we care? And the reason we care is that our theory of quantum mechanics tells us that we must preserve information. The theory of quantum mechanics preserves information. And if you don't preserve information, then you don't preserve probability. That means that the probability of something happening can be greater than 1, whatever that means. Or the sum of the probabilities of all possible things happening could be less than 1, and we don't really understand what that means. Quantum mechanics requires that the total probability of all possible events is always 100%. Never more, never less. And it tells us how that happens. And it doesn't happen when we throw things into a black hole. So quantum mechanics tells us that information is preserved, and general relativity, the theory that describes black holes, tells us that information is lost. Now here we have our two most successful basic theories of nature. And they are fighting it out. One says information is preserved, and the other one says no, information is lost. And they're duking it out, but that's not very good, because we need to come up eventually with a theory in which they shake hands, in which they work together. And we don't know how to do that. And it's one of the most basic questions in fundamental physics. How do we put together general relativity and quantum mechanics? And part of doing that is going to have to be understanding the information loss paradox. So I've told you lots of things about black hole. There are many more things to say. And what you should come away from this is that black holes are fascinating, but they're also mysterious, not just to people, but also to physicists. Thank you very much.